Hello, everyone, and welcome to our second session of the day. We've got Z16 capacity planning with Danilo. Could I ask everyone to check that their microphones are muted? Myself and Danilo. I'll hand over to Danilo in a second. There'll be time for questions at the end, but I'm sure Danilo will find if you've got questions partway through. Danilo, over to you.
Okay, thank you. Can you hear me?
I can hear you loud and clear.
Okay, thank you. Good morning to everyone. I am Danilo Gipponi from EPV Technologies. I cannot see who is in and who is not, and I hope many friends will be there. If not, well, at the end of the session, I will show my face. This is a live session, so I'm talking right now to you. And just one word on this first slide. It's now 20 years that EPV Technologies is on the market, so that's why this 20th anniversary on top of the slide. Let's go to the discussion of the day. And again, if you have questions, comments, please feel free to share them. I would like to have a live session, even though it's very difficult when we do this kind of things virtual. By now, we know that people is shy on the other side, but anyway. Okay, so this is a paper titled Z16 Capacity Planning, and it starts with this kind of premise. Last 5th of April, IBM announced its new generation of the mainframe. So it's incredible. It's almost a year that this happened. Anyway, this new system is called the IBM Z16, and the family model is 3931. Now, everyone that works on this kind of activity for some years knows that whenever there is a new generation of a machine, this will change everything that is behind. And by the way, this is one reason why we do not do modeling, because it doesn't make any sense, because you do a model on a machine and then the new machine comes up and it's completely different. And so what happens is that when new machines are announced, you have to understand how they work and see how can you better exploit them. In this very case, this is especially true because the changes to the cache architecture that we will discuss later has been, let's say, a giant step forward. So this is really a new, let's say, a new step in the right direction. So at the beginning, we will make some example on how these things are going to change compared to the 3 previous families, the Z13, Z14, and Z15 machines. Okay, this is going to be the agenda. So in the next hour or so, I will discuss about the capacity highlights, about the Z16, discussion about MIPS and MSU on this new hardware, then the capacity of a single general purpose, and then the variability of the capacity. Very important, the cache architecture that has been really changed. And then something about level 1 MIS and RNI, so how to do capacity planning literally. And finally, the last point will be cycle per instruction. Okay, so this is the first chapter. Before I go forward, I remind all of you that probably most of you already know, there is a white paper, really a paper, a document written, a PDF, where you can find all the details of what I'm trying to discuss in the next minutes. So if you are interested in that, either you let me know, or you let know Nathan, or anyway that you can share, and we will provide it to you. Okay, so in this first table, we make some comparison about the Z16, which is the latest hardware produced by IBM, Z15 and Z14. And I'll again, these slides are for you already on the site, so you can download them, so you can have this table on your PC whenever you want. I will just focus on the things that I believe are most interesting from my point of view. First of all, the cycle rate. You see that the cycle rate in gigahertz didn't change when you look at the z16 and you compare it to the two previous families. So the clock speed of the CPU is exactly the same. There has been some changes in the architecture, though, and with this new hardware, you could have configure up to 200 general purpose. And this is something that is, let's say, completely out of reach for most of the companies, but there are a couple of companies that are on those figures in the world. So let's say that from the architectural point of view, they can still grow their capacity. The number of LPARs that you can configure on an hardware are still the same in this last regeneration. And as it was true in the two previous families, also in this one, you have sub-capacity models, which could be very interesting for medium or small enterprises. And if you do not understand what I mean by this, or if you do not know what sub-capacity models are, then I suggest you put forward a question now or later. So I will eventually discuss that. Okay, so when you see the entry MIPS, it's greater than the previous. So there is still an increase in their hardware. The maximum MIPS that you can have online is greater. That is mostly due because of the fact that you can now configure your machine with 200 engines. And so every single engine we saw the previous row is great, is bigger, it's more powerful, but then you can even have 10 more available online. And this goes forward again with the MSU and the max MSU. Two more comments, interesting. First of all, that the memory has not had a change, but 40 terabyte is a huge amount of memory. So there are, let's say, that is not where IBM focused their development in this last time. And the other thing that could be interesting and will be probably interesting sometime in the future is the fact that the simultaneous multi-threading is not available for general purpose, not yet. And this is definitely a technical decision. It's not, how can I say, potentially they could do it if they wanted to, but they decided not to. And I can say why, but this is the way it is. So we reprise some of the things that I said looking at the previous slide. So it's worth to note that even though the clock speed is the same, still the biggest model is bigger in potential capacity providing to customers. And again, this thing is probably going to be interesting for only a couple of companies right now in the world, but still, let's say that the overall capacity is still going to increase. So IBM has an eye on that. And finally, again, SMT is not allowed. Okay, so we move forward to the next chapter if there are no comments or questions or anything. So the same day that IBM announced the new hardware, a new set of LSPR benchmark have been published on the web. And let's say that you see in this slide the link where you can go and eventually reach these published benchmarks. And what else to say here? That on these benchmarks, if you really put some attention on it, everything up to the Z15 did not change. So they didn't make, in the past, sometimes when they publish new benchmarks, they do some minor changes to the previous definition. This was not real this time. So everything up to the Z15 stays as it was. So the benchmarks up to the Z15 looks to be very clever. And what you find new on when you go on this link is that the new family has been added. So you know how they will behave or how they are supposed to behave. As usual, you have three benchmarks, three workload categories: low RNI, average RNI, and high RNI. RNI is an acronym for relative nest intensity, and it tells you when you are in a critical situation, when you cannot find what you're looking for, or better, when the machine cannot find what she's looking for in the first two levels of the cache, she will go further away, and the more you go further away, the more you affect the capacity that the machine is going to deliver. The very strange thing or funny thing about this situation is the fact that when you really look at the numbers, at the figures, especially in production, generally only 3% or anyway less than 5% of the situation cannot find what they are looking for in the first level of the cache. And still, this minority of situation is the one that really determines how much capacity your hardware is going to deliver in your configuration. And what else to say about this slide is that nowadays, in our experience, most of the production helpers fall in the average RNI category. But again, this is something that you can really well measure, and this is one of the statements of this presentation. You can measure and you can know exactly where you fall. And I will say some more words about this in a few slides. Okay, benchmark are the ITR ratio between the capacity of the new model and the capacity of a reference processor, which is the same for years and years. So there is the possibility to understand on every machine how many MIPS you can provide. And again, there is, let's say, there is nothing new on this slide compared to what has been the reality in the last 20 or so years. So I will not spend any more time discussing it. I leave it to you, again, in the documentation. And again, if you have questions, I am here. So, but this is something that I assume everybody understands. Okay, this is an example taken from the LSPR benchmark that I told you. And we see the first lines, then there are some dotted points, and then the last lines. So the last lines are those that refer to the Z16. Again, the one thing that I always try to let people focus their attention to is the fact that when you look at the last line, and that's just an example, just really to say what I point out in these few statements. The last slide is an hardware. So you have let's suppose that you have that machine with 200 engines. Now, depending on your configuration, your workloads, your settings of the weights and things like that, you could fall in the low MIPS column, so the low RNI, or the average RNI and the high RNI. And when you look at the figures, you see that the difference between the higher NI and the lower NI is 70,000 MIPS. 70,000 MIPS out to 260,000. So it's a huge difference. In other words, if you are very accurate in your definitions of the weights you can influence these figures, and you may have, as a result, the fact that the hardware that you just bought or that you are going to buy will be more productive in terms of capacity, in terms of power, or less, more or less. And let's say just here, if you remember when the Z13 came up the first time, the Z13 family, well, in that family, the definition was so critical that IBM came up with tools explaining to people how the weight could change the effect on hyperdispatch, on other things, in order to explain to you which was the best configuration. Now, that was eclatant in Z13. That was a huge problem for IBM. IBM addressed that, and that became less and less important with the next machine. So the Z14 addressed that issue. The Z15 even better, the z16 even better. Still, when you think about it, if you do changes in the way you configure your helpers, in the weights, in the, let's say, general behavior, you can affect the result on the hardware. So practically speaking, your machine can deliver more or less MIPS depending on the definition, on the configuration that you make. Oh, this is another thing that I like. So these slides represent the ratio between MIPS and MSU in the last version of the hardware. And then again, you see that there is a slight difference when you are on small configuration, or small eventually from the IBM point of view. But when you have a situation where you have at least 30,000 MIPS installed in your place, then at that point, the ratio between MIPS and MSU becomes very constant. So what is the line behind this statement? Is the fact that MSU are measured by RMF or are evaluated by RMF. So RMF make an evaluation and write it down in SMF. So based on what is written down by RMF in SMF, you may state how many MSU you are really using. And based on that figure, you paid your software in the last years. Historically, people used MIPS to understand the capacity of their installation. And MIPS, it's always been an evaluation. So you start with a figure, probably you start from the LSPR table or from the Gartner tables or whatever figures you have in mind. And starting from that number, you decide how many MIPS you are going to deliver. But this was an estimate. And now this graph tells you that this can be overcome in practical terms. So there is no statement anymore. There is a straight relation between the MSU consumed by the latest hardware produced, at least from the last 8-9 years, and the MIPS. So you may say that you measure the MSU, you multiply per 8.5, and then you get a very good estimate of the MIPS that you are going to deliver. Okay, some words about the capacity of a single engine, a single chip. You see that the figure is varying. So in this graph is represented the difference between the previous generation and the next generation. So it was huge from Z9 to Z10, then a little less, and now it's stabilized, and every new version you have something close to a 10% increase. This is mostly due because we are approaching let's say, the real exploiting of the hardware material that is available to IBM. So anyway, still you see that there is a growth in that respect. So things are improving. About this slide, I just let you read the first two rows. On the third row, I say what I said in the premise, that NICAP models could be very interesting for those environments that are not very big. And the reason for that is because the fact that there is a mechanism that will reduce the clock speed of the general purpose. But when you have special engines, the zip engines, they will go at the full speed. So in that way, you can configure a machine that will have much more capacity that could run on a zip and spend less in terms of software costs. Okay, more CPU, there is more processor cache, and better hyperdispatch exploitation. Hyperdispatch still is not yet mandatory, but I believe it will be soon because it makes no sense not to use hyperdispatch. And again, some figure compare of the subcapacity models, the NICAP models, and they all increased in a way when you move from Z15 to Z16. Okay, the other thing we like to always have a look at is the capacity variability. And what let's say, this is the definition that we give to capacity variability, and the formula is very simple. So we take the capacity that can be delivered when you look at the PCI tables that we saw before. If you are in a lower NI configuration, that's the best position always. We subtract that to that the higher NI configuration. It means that the same hardware can deliver much less because there is a lot of contention, or anyway, the cache memory is not exploited very well. And we divide that by the average value. So it's very simple as a concept. And this is the result. And what you can see here is that it's still huge. And again, it's what I told you before when we saw the last line of the PCI table, that let's say in the best configuration, you could deliver 260,000 MIPS, and in the worst, only 190,000 MIPS. So that is what we are talking about. So it's still huge, but you can see that IBM is moving in the right direction. So they know this is an issue, and they are, with every new release, addressing that. And they are really literally moving forward. So on this respect, I have to say nothing to IBM. So we are still at the 32%. That's the difference between those two values that we saw before. And that's really, let's say, in the highest class of hardware that you can install. But you can do this kind of calculation for every machine that you install, and you can understand what could be the difference in your situation if you run and you exploit the machine in the best or in the worst way. So again, the bottom line is very important to classify your system workloads, your configuration, your weights. You have really to spend some time thinking about the best configuration that you can design and use it, because you can have advantages. But by the way, I say here something that is not really connected to this, but just as a reminder, the good practice says that every time at least every time that you change the hardware. So when you move from a previous class to the next class, at least in that moment, you should review your workload manager characterization and definitions. And you may have advantages in doing that. I know, because of the way life is, it's always on a run, and not many people do that, but you should think about it. Anyway, let's go forward. The other statement from this slide, in order to understand how you are exploiting your hardware, you need to have the record 113. This is something that is now available for some years. The overhead is negligible. The value is huge. So you should turn it on every single helper on your at your home, because it makes sense. By the way, if you have issues, IBM will ask you to turn it on. So there is no reason not to turn it on always, because the overhead is negligible, really. You will never notice that you turned it on. And the value you can get out of it is huge. And the other comment we always make is that there is a very interesting tool. It's a free tool done by IBM. It's called ZPCR, and that can help you design, let's say, model different configuration and see which one can provide the best exploitation of your hardware. Now, processor cache architecture. This is the most relevant change probably when we look at this hardware and compare to the previous one. So when we look at the Z16 and compare to Z15 and the others, when you look at it from the logical point of view, Z15 and Z16 are very similar. There has not been dramatical changes. What happens is that either you find what you're looking for in the level 1 cache, and that it will be a cache hit, and that's the best case, because you will not waste any cycle. And if not, then there is a logic that must be followed in order to find out what you're looking for. So if you do not find what you're looking for, a data and instruction in level 1, you will try in level 2. And this is something that is very, very close to your chip, and still it's not in the nest. So everything that is missed from level 1 and is found on level 2 will not affect the RNI index. So again, level 2 is not as good as level 1, but it's definitely better than level 3. If you do not find what you're looking for in level 2, then you have to go forward, and you go forward trying what you're looking for in level 3, in level 4, then the level 4 from a remote drawer, then in memory, and the worst case is remote memory. And what is the bad situation here is that whenever you don't find what you're looking for in level 1, then your CPU is spinning, waiting for the system to fetch what it's looking for. And again, if you find it in level 2, it will waste few cycles. But the more you go further away, the more cycles will be wasted with the engine spinning, so wasting cycles, literally, waiting for the information to arrive. And meanwhile, the system will try to get it in the best position it can. So if it can from level 3, otherwise from level 4, and blah, blah, blah. So this is, in a way, incredible, because, as we said before, in a production system nowadays, you have a 97% hit, and only the 3% that you are missing will create all the disaster, because that is really what it is. So all the wasted power will be just because the cycles are there, wasted, running on in a loop, waiting for the information to come, to arrive. And if possible, this is what you should try to avoid. Okay, I said a lot on the previous slide. Anyway, when you make a cache miss, blah, 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 you waste the cycles. And as I said, the number of lost cycles depends where you find what you're looking for. Okay, that is the theory. And the theory in Z16 hardware didn't change compared to the theory of what was happening on a Z15 or previous versions of the hardware provided by IBM. But physically, something now is different. On a Z16, first of all, the maximum of drawers is 4 instead of 5. And just the fact that it's 4 instead of 5, let's say statistically, we reduce the possibility to find what you're looking for in a drawer that is remote from where you are starting, because there are less of them. So it's statistically more difficult to get there. But apart from that, there are still major changes. In each drawer, there are 4 dual chips instead of 2 clusters. And in each chip, there are 8 cores instead of 12. And this is a comparison between Z16 and Z15. To my mind, the very, very, very huge change is the fact that the level 2 cache is much bigger when you compare the Z16 to the Z15. It's now 32 megabytes. And you have to consider that if you find what you're looking for in level 2, that is still not affecting the RNI index. So things are really going not in the best, let's say, not in the best situation, but definitely you are not entering the nest. So that is very good. And this level 2 cache now includes both instruction and data. And there are 2 parts. One part is called semi-private. So the private part is dedicated to the processor, and the non-private part is used to virtualize level 3 and level 4 caches. So the statement is level 3 and level 4 caches are virtual now. They are not physical as they were in Z15, but because of the architecture, they can, let's say, level 2 is definitely much bigger. And in theory, even level 3 and level 4 could be, if not the same, even eventually bigger than the previous hardware. Now, this is something that can be discussed at length, and even IBM is let's say, it's on the gray on this statement. So it's not black and white. It looks like more of a marketing statement than the real technical one. Still, the point is the architecture has been changed, and the effect of this change on the behavior of your workloads against the hardware looks to be very, very good. This is, let's say, true in theory, but also practical installation that we saw, recent installation looks to show this kind of advantages. Okay, so let's have a couple of slides of what is today. And so this is at Z16. So you have physically level 1 and level 2, and you see level 2 is now 32 megabytes. So it's really, really, really huge. And then you have level 3 and level 4, which are virtual. Compare this slide to the next one. This was the previous hardware, so the Z15. So you see that the level 1 is practically the same. Level 2 moved from 4 mega to 32 mega. So again, it's 8 times bigger. So you have 8 times less possibility to enter into the nest. And that's a huge, huge step forward. And still, when you look at the nest, in the previous hardware, that was physical. So you had a real level 3 and you had a real level 4. And again, if I should go back to the previous slide, if I am able to do it. Okay, here I am. You see that the level 3 and the level 4 here as virtualized, so you don't really know, but you can measure how they are behaving. And again, let's say the first experience we had with our customer show great improvements. Okay, this is written down what I said before. So there are some statements from in the documentation that looks really on the grand side, and maybe it's true, maybe not, but still the very good thing is that you can measure it, and when you can measure the behavior of your hardware, you may at the end make a statement, yes, it's better or not. And then again, our experience so far is that Z16 is working very, very well compared to the previous hardware. So it's really going again in the right direction. Okay, this is, let me read with you this slide. We said before that the level 1 miss that you find when you measure a production system, even in a Z15, are, let's say, between 3 and 5%. Generally in production, they are close to 3%. And when you move forward, 70% of these 3% are insourced from level 2. Okay, let's say that based on the first figures that we have, I could say that we are going to change these figures in the future, talking about of these 3%, around 90% are insourced in level 2, because that's what we saw. But still, we have too few real life examples to make that as a general statement, but that's the feeling. Anyway, the reason why IBM is trying to improve the heat in the level 2 cache is quite evident. And again, because if you find what you're looking for in level 2, you are not entering the nest. So that is not affecting in terms of behavior your machine. It is, but it's not affecting as much as it could be. Okay, this is not changed, at least in theory, compared to the previous version of the hardware. So you have to calculate level 1 miss and the RNI. In order to do that, you need to have the record 113 turned on. If nothing else, when you come back home, if it's not turned on in all your helpers, make that change, turn it on. There is no reason not to do it. Now, since they introduced the record 113, basic counters had always the same meaning and never changed. Instead, the extended counters had a back habit for end user, and in a way a good habit for companies like mine, because every new version they change something, and it's very difficult to stay tuned on the changes, and that's what we do. So there is a field which is the 113 CTR version 2 that has a figure. If it's 1, it means it's a Z10, and so on. You may read it. So you have to read the record, read this field, and then enter in a different section of loops depending on the hardware that you have behind. Because again, the extended counters, the same counter has different meanings depending on the hardware that lies behind. Basic counters, again, are the same as they used to be. So to calculate the level 1 miss percentage, it's very easy, and the formula didn't change. And here is explained in this slide. The relative nest intensity is a measure of the activity to the nest, and the nest starts from level 3 and level 4 and the memory. And it's the one thing that is really affecting the capacity that your hardware is going to deliver. With every new machine, IBM provide a new formula, and in a couple of times in the past, they changed the formula after a while. So this is not true so far for the Z16. This is the formula that has been announced by IBM. And you see that you have to wait the percentage of a situation where you go in level 3, and then level 4 local, and then level 4 remote. Anyway, this is the formula. In the next few slides, I will not really read not all the slides. I will leave them for those that are really interested in doing this kind of thing for themselves. Anyway, when we talk about percentage, level 3 is the percentage of level 1 misses that are sourced at that point from the level 3 cache. Then there is L for L. In our next slides, it's what we call insourced from level 4 local. Then there is the level 4 remote, and finally the memory. How do you calculate them with a z16? These are the fields that you have to use and the formulas that you have to use. So how do you count the number of data that is sourced from level 2? You have to take the two columns, extended field 145 and extended field 146, and sum them together. The instruction are the two extended counters, E169 and E170, and so on. So you see the formula for every single different place where you did get the data that you missed from level 1 cache. This is logically following the previous slide. So if there are no questions, I will just leave it to you to read quickly now and then eventually to study that later with the slides. So first of all, you have to calculate those fields. So you have the percentage of level 2, the percentage of level 3, the percentage of level 4L, and blah, blah, blah. How do you get to them? You do the formula of the previous two slides. Then you do the formula on this slide. And finally, you apply that to the previous formula that we saw, that is the one that you have to use when you are looking at the Z16 machine. So how do you calculate the RNI? You apply the formula. I will go back a few slides very quickly just to... So these are all the things that you have to calculate. And when you have them all in a piece of paper or in a spreadsheet, finally, you have to use the formula that is the last line of this slide. So in order to calculate the RNI, you have to multiply 4.3 multiply open bracket blah 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 level 3 plus. So you apply this formula. In the end, you will have a number. How do you use that number? You use it in this table. Is this number is greater or equal to 0.75, and the level miss of the first level of the cache miss is less than 3%, then you are in an average RNI. And again, in our experience, this is the benchmark representing most of the customers in production. And then, again, it's very simple. You apply the formula. So where are you with the level 1 miss? It will be one of these cases. At that point, where are you with the RNI? You will be in one of these cases. Depending on the combination, you may state that that is an L part that is running in average RNI, low RNI, and so on. So your workload will exploit in a good or in a bad or in an average way the hardware that lies behind. Final chapter, cycle per instruction. Cycle per instruction, CPI index represents the average number of cycles needed to perform an instruction. It's calculated using basic counter, so it's very simple and it didn't change in time. So CPI is something that is available for some time now. There is not a rule of thumb for the ideal CPI value, but of course, the lower it is, the better it is. So if every time you do an instruction, you just need one cycle, at that point you would exploit the machine really, really in the best way. If you do an instruction and you take 20 cycles, so let's say it's clear that you are somewhat losing the power of the machine in some way. Generally, CPI is used to evaluate the performances when you move from a previous hardware generation to the next. And let's say that there has been a problem in the past, but this is not going to be the case right now. If the clock speed is different, then this will affect the cycle per instruction, because if the clock is faster, there are more cycles in a second, and if the clock is lower, there are less cycles. So you have to take care of this thing eventually, but this is not true right now because the clock speed has not changed in the last 3 generations. So just be aware of it, and that's it. Then the last thing to say about cycle per instruction, that they can be divided in 2 different measures. One is the finite, and the other one is the instruction complexity. Okay, let's say the first one is if you would have an infinite cache and you need to perform an instruction, still you will have to use some cycles. That's because you have to do something. So at least one cycle you will have to do, and probably more than one. And that can be defined as the finite CPI. The other one is the instruction complexity CPI, is the one that is affected by the architecture that lies behind. So the more the architecture is performing, the lower this will be this part when you measure the CPI. I have to say that this is a very theoretical statement. It's probably useful to IBM developers and not for final customers. Anyway, it's there, so you know that there are these two things. So the formula is the same because we use the same counters. So in this case, even the extended counters didn't change. And that's the end of this section. So we are at the summary. Many changes introduced in the z16 processor or cache. Every time there is a new machine, there is a lot of excitement. This time the excitement looks to be well reposited because first experience of customers show very, very great improvements. And again, the z16 is moving in a new direction. Of course, always when you move from a family to the next family of hardware, you have to take care very carefully in capacity planning. And that is my last statement. Are there any questions, comments? If not, this is the end of the presentation. And maybe, if I am able, let me see.
Thank you, Danilo. Does anyone have any questions for Danilo? And Danilo, do you want your email address on screen? Possible, so people could send you.
Okay, my email address was in the first slide, and the slides are on the site of the UK share, so you can download them. Let's say that the most important thing I really can say is that there is a white paper behind this presentation.
We have a question, Danilo. Can you see it in
Yes.
the chat?
No, can you read it for me, please?
Any concerns if workloads moving from Z15 to Z16 and then back again in a few months due to multiple plates?
I'm not sure I understand what's the meaning of the question. So you are moving from a Z15 to a Z16, and then you are moving back again. Is that the question?
Seems to be BMS, which is there. Can you clarify your question at all for us, please? I'll read it again, Danilo. Any concern?
Well, let's say that anyway. Again, I'm not sure I understood the question or what lies behind the question, but the point is that, let's say, my suggestion is this: the very, very good thing you can do with this in this situation is that you can measure. And even though the measurement is not made easy by IBM because they changed the extended fields and everything, when you register the record 113, you may really classify what's happening to your workloads. So again, we have few, not many. Let's say there are many, many companies amongst our customers that are planning to move to Z16, but let's say the general time frame is before summer. So very few did it already. And one thing I can say for those that did it already is that they had improvements, definitely, at least in the figures. Let's say that the figures were what they were expected to be. The general feeling doesn't always match the figures. So the figures are better. The general feeling is that the improvement is not as good as the numbers are. And then again, why? It's too early to say. We need to have more figures and not numbers. And for sure, the fact that the level 2 cache is so much bigger, this will decrease the RNI by definition. So the RNI is going to be lower than before. And this is, in terms of, again, numbers reported, a very good thing. Then, if I have to add something to this statement, is the fact that because now MSU and MIPS are so tied together, so there is a number that is really a ratio between the two of them. MSU are measured by RMF or estimated. I don't know how RMF calculate the MSU, but still they are written down by RMF. So whereas MIPS has always been an estimation, so they start from a figure that is provided outside of the system. Instead, MSU are measured. Then the one thing to do is to look at MSU, use them to have a MIPS, let's say, figure and see if this corresponds to the expectation. That's my suggestion. And then if you move back, well, I don't know. I can't imagine why you would do that. But again, if BMS can want to talk to me privately, maybe he doesn't want to share this thing with everybody. But
we've got some clarification, Danilo. We said upgrade one CPC and site one. But if we
okay.
site swap the CPC, may still be Z15.
Yeah, well, let's say now, okay. Sorry, now I read it and I may understand what is behind the question. And unfortunately, I cannot provide an answer to that. So here we talk about theory and practice. So in theory, things should happen in a way. In practice, you never know. So let's say, anyway, the only implication in this situation could be that the same workload behaves completely different in the two types of hardware. And if that is the case, yes, then you could have probably a situation where, let's say, the same group of address spaces consume a certain amount of power in one configuration and a different amount of power in a different configuration. But it's very difficult for me to forecast that. It's something that you have to measure. I'm sorry.
Do we have any other questions for Danilo from anyone else before we end the session?
I'm moving forward, if you notice.
Get you stepped in, Danilo.
No. I prefer, if you don't mind, I can turn off my video. So,
well, we've got no more questions, so I think we'll end the session there, Danilo.
Okay. I hope you like the session. And again, I am available. And if, let's say, if you will not be able to reach to me, you can go to Nathan or to GSC Share and let them put forward your question to me. I'm willing to exploit whatever I can about this topic. And
as Danilo mentioned, you can download his slides from the GSC website. So,
yeah. Again, there is a paper that is a physical paper, so you can get it on request.
Mm-hmm. Okay, well, we'll leave it there. Thank you, everybody, and thank you, Danilo. Danilo's got another session tomorrow, so we'll see you all. And we've got our next session later today after the lunch break, so see everyone soon. Thank you.
The session tomorrow is going to be much more focused on something very, let's say, narrower. So I would expect to have less people, but you never know. Okay, thanks a lot of you guys for staying with me in this hour.
Yeah, thank you, Danilo, and see everyone in an hour for the next session.
Bye-bye. Ciao.